Here it looks like we have speakers playing the same frequency, which I think we don't know, right? We don't have any information on the frequency yet. I guess that's what we're trying to find in the end. What is the frequency? So frequency is currently unknown, but we can figure out, actually we're gonna need the total phase here. Let me go copy paste the variables we're gonna need there. So we're gonna be using total phase anyway. I'll just paste that in for future reference. And in this case, we know that when he's standing exactly in the middle, he hears almost no sound. I think we can interpret that as basically destructive interference. So what does that tell us? If we know that he's hearing no sound near the center. What type of interference does that suggest?
Would it be destructive?
Yeah, if he's hearing almost no sound, that is definitely destructive interference. And if he's standing in the exact center though, what do you know about the distances traveled by the two sound waves? Yeah, they're equal. We've got wave from wave from speaker 1, wave from speaker 2. Right, those are traveling the same distance. In this case, they're both traveling 4 meters. So there's no difference in path length. Delta X is gonna be 0. And that tells us something very important. If he's standing in the exact center, so there's no difference in path length, what type of interference would you usually expect if there's no difference in path length? Yeah, usually I would expect constructive interference, but he's hearing destructive interference instead, and that means there must be something else going on. So what else could be happening to turn what we'd expect to be constructive into destructive instead? Right, they've got to be out of phase. And specifically out of phase by how much? I would expect, well, how much of a cycle do you have to go through? What fraction of a cycle do you have to go through to convert from constructive to destructive? Like if you've got two waves that are precisely lined up, that's going to be constructive, right? If you want to get it exactly out of phase, lambda over 2 would be it if we're talking about distance. But here we're not talking about distance because we know there is no path length difference. What fraction of a full cycle would that have to be? Yeah, half a cycle. And if we're talking about radian measure, 1 full cycle is 2 pi. So half a cycle would be half of 2 pi, which is pi. So we should expect these to be, in terms of radians, we should expect these to be out of phase by pi in order to be destructive. So that means the delta total phase is pi, or 3 pi, or 5 pi, or 7 pi. Any odd multiple of pi is something and a half cycles. But in this case, there's no difference in path length. So going back to the total phase difference equation, there's no difference in path length or wavelength. There's also no difference in frequency because they're both producing the same frequency. So the only difference that can even exist here is a difference in little phi, the phase shift. So if we have destructive interference, the difference in total phase is pi. Therefore, the difference in little phi, the difference in phase shift, is also pi. And as someone said earlier, that presumably is because the speakers are wired oppositely. You've got one of them with positive plugged into positive and negative plugged into negative. The other one, the wires are reversed, which means the speaker's membrane inside is pushing when it should be pulling and pulling when it should be pushing, creating crests instead of troughs and troughs instead of crests. So I think we can conclude here that the fixed phase constant difference has to be either pi or any odd multiple of pi, but it says just pick one. So we'll use pi. So that'll be our difference in little phi. Difference in that difference in little phi is going to be pi. Any questions on that so far?
For like if something similar was on the exam, since we'd probably have to like provide some sort of explanation, would we just kind of restate how like based off the diagram we would expect like constructive interference, but it says he hears no sound. So like to make it destructive, there has to be that pi difference.
Yeah, as an informal way of putting it, I think that would be fine. The test itself might want something a little more formal in terms of the explanation though. So, I mean, I think it's a good idea to be able to look at situations like this and develop more of an intuition for it. Like in this case, I look at this and I think, oh, the waves are traveling the same distance, so they should be constructive, but it's destructive instead. That means there's got to be some sort of phase shift, and a phase shift that takes constructive to destructive would be half a cycle. So that's how I think about this more intuitively. But if we want to make it mathematically formal, either if it's not immediately obvious by looking at it, or if you need to demonstrate conclusively that, yes, we know this to be true, in that case, we want to go back to the total phase equation. And setting up a phase chart can be a useful way of organizing the information there. Excuse me. So if we split this up into, let me make this a little more legible, into the time term, the position or distance term, and the phase shift term. And then we want to compare waves 1 and 2 and the difference. Although I guess we don't really need to worry about waves 1 and 2 individually. We could just look at the delta. So we know these speakers are pumping out the same frequency. So the difference in frequency is 0. One moment. Correct answer would be total phase. Yeah, we could essentially use any odd number times pi. Because if it's destructive interference, that just means the difference in total phase is something and a half cycles. But we could use any odd number times pi as long as we're consistent about it. So I would just use 1 pi because that's half a cycle. So if we start filling in the values here, we know there's no difference in frequency. And of course, the waves are arriving at your ears at the same time. In this particular case, there's also no difference in path length. The waves are traveling the same distance and they have the same wavelength. But we know that there's a total phase difference of pi because it's destructive interference. And the only way for this to work then is if the difference in little phi is also pi, because 0 plus 0 plus pi equals pi. Any questions on that so far? So I would say that that would be an adequate way of explaining why we know that the difference in phase constant is pi. You'll probably want to write a sentence or two explaining what you're actually doing as well. But the key idea is that using this phase chart as a way of organizing the information, we know they're the same frequency and arriving at the same time, so 0 difference there. We know they're the same wavelength, and in this position, they're also traveling the same distance, so no difference there. We know that the difference in total phase has to be pi, or some odd multiple of pi, because it's destructive interference. The only way to achieve that is for a delta little phi, delta phase shift, to be pi also. And again, we could explain that by saying, or justify this physically by saying, presumably the speakers are wired oppositely. Any questions on that so far? Then let's take a look at part B. It says he walks 3 meters to the right towards speaker 2, and he hears the sound of his 2 speakers get louder, then quieter, then louder again. So after 3 meters, he's at a point of constructive interference. And we want to find the frequency here. And the louder than quieter than louder again thing, I think might be making this kind of tricky. So let's focus on what's going on as he walks, because it's not going to be same distance anymore. What we're going to see here is that as he moves 3 meters, so his new location is going to be here. At that new location, just 1 meter away from speaker 2, he hits a constructive interference. We're going from quiet to loud to quiet to loud. So let's actually mark all of those locations. We're going to have probably evenly spaced. If we think of these as loud, quiet, loud, quiet. So I'm just going to mark the quiet zones with these empty rectangles and these loud zones with these filled rectangles. I should probably remove the picture of the guy also, so we can actually see it a little more clearly. So we get this alternating pattern of destructive, constructive, destructive, constructive, which it specifies in this problem by saying, as he walks these 3 meters, he hears sound get louder, then quieter, then louder again. So we could think of these as destructive, constructive, destructive, and constructive interference again. And we know that this final constructive interference spot where he stops is 1 meter from speaker 2. So we could actually fill in some path lengths there. 1 meter from speaker 2 means how far from speaker 1?
Wait, sorry, is the leftmost like box where the person is originally?
Yeah, so this one in the center here is the destructive spot where he started at. And then the problem says he starts walking to the right. And as he walks, he hears the sound get louder, so that's constructive, then quieter, so that's destructive, and then louder again, that's constructive at this location. He's walked 3 meters to the right. He's now only 1 meter from speaker 2, and yes, he would then be 7 meters from speaker 1.
Okay.
So we at least know at this last constructive zone where he stops walking, he's 1 meter from speaker 2, 7 meters from speaker 1. So what would delta X be there? Yeah, 6 meters of difference at this one location. So we know that at that location, delta X is 6 meters. And let's see if we can fill in the rest of the chart. Because we had a row in the chart for the center. In fact, let me mark that here. That was at the center. But then we're going to look at this new location. This new spot that he moves to. There's still no difference in frequency or time because both speakers are pumping out the same frequency as each other and they're arriving at his ears at the same time. But there is now going to be a delta X term. There's a difference in position of 6 meters because one of the waves is traveling 6 meters further than the other. So we're going to have negative 2 pi times delta X would be 6 meters. And do we know the wavelength here? I think wavelength is unknown, right? We don't know the frequency and we don't know the wavelength. So I'm just going to fill in wavelength as an unknown variable. So this x term, negative 2 pi times delta x, which is 6 meters, divided by wavelength. And can we fill in a delta little phi, delta phase shift?
Would we say that it's the same thing, or would it be different, like from part A?
Good question. Is this the same or different? What causes the phase shift? Why did we have a phase shift in the first place?
It would be like the wiring, right, of the speakers.
Right. And as he walks, is the wiring of the speaker changing?
No, right?
Right. So we should expect that to be the same. The delta little phi depends only on the sources. It doesn't depend on where the observer is standing at all. So we should expect that to be the same. The only time that's going to change is if these sources themselves change. But we still have the exact same sources. The only thing happening is he's moving to a new location. As for delta big phi, we know he's at a constructive interference zone because it's loud again. What does that tell us about delta big phi?
It has to be an even multiple of pi.
Yeah, got to be an even multiple of pi to get constructive interference. And in many cases, we might just say that's 2n and try and figure out what possible values this could be based on n. And yeah, 2n pi would be a good way to write that. However, in this case, we can be more specific about that because this isn't just any constructive spot. This is one very specific constructive spot. We know we've just gone from destructive to constructive to destructive to constructive. So we can actually mark off which one has which delta total phase. And we can do that by taking a look at these values we had here. That very first destructive spot in the center, what were we calling the delta phase for that? At the very beginning, that one in the center, we were assuming, I mean, that was destructive. So we were assuming the total phase. Yeah, we were assuming that was pi. So if we walk from that destructive spot to the very next constructive spot, what's the very next constructive spot?
Be 2 pi?
Yeah, because 2 pi is the very next even multiple of pi. Then we walk a little further to get to the next destructive spot. What would you expect the total phase difference to be at that next destructive zone?
3 pi?
Yeah, because that's the next odd multiple of pi, the next something and a half cycles. Continue a little bit further, what would this constructive zone be?
Four pi.
Yeah, the next even multiple of pi, the next whole number of cycles would be 4 pi. So we can associate each constructive or destructive spot with a specific value of delta total phase. Odd multiples of pi for the destructive zones, even multiples of pi for the constructive zones. So I think because of how many loud, quiet cycles we've gone through by walking this distance, we can label this 4 pi. So it's not just any even multiple of pi, we can specifically call that 4 pi. Or alternatively, we haven't really been very formal about directionality here. Maybe we're going from pi to 2 pi, but what's another even multiple of pi you can get to from pi? Like what's another even multiple of pi that's right next to 1 pi?
0?
Pi?
Yeah, maybe instead of increasing the delta phi, maybe walking in this direction might be decreasing the total phase.
Sorry, why would we have to consider that? Why can't we just use the 4 pi?
The thing is, the idea that total phase is increasing as we walk in this direction is kind of an arbitrary guess. It might be the case that as we walk to the right, total phase is decreasing. And this really is going to depend on which order we're subtracting. Are you subtracting 2 minus 1 or 1 minus 2? And if we got +6 for the distances, presumably we're subtracting x1 minus x2, 7 meters minus 1 meter. So I don't really know, unless we actually run the equations on this and try some examples. I don't know if, as you walk to the right, we're increasing the total phase or decreasing the total phase. Because really it's about the difference in total phase. Are we subtracting 1 minus 2 or 2 minus 1? So we should probably consider both possibilities just to make sure. I'm guessing that in the end, one of them is going to make sense and the other one's not. But I would consider both possibilities. Because ultimately the difference is, are you subtracting 1 minus 2 or 2 minus 1? So maybe we go backwards. Maybe we get 0 pi, because that's also constructive interference. Keep going. What's the next destructive interference going to be?
Be negative pi.
Yeah. And then we keep going again. What's the next constructive interference?
Negative 2 pi.
Right. So we should probably consider both of those as possibilities. Let's start by just saying, assume it's 4 pi. If that doesn't work, we might try negative 2 pi. But let's try this out and see what we get. Writing this out as an equation, we should be able to just say negative 2 pi times 6 meters over lambda plus pi equals 4 pi. And then I think we should be able to solve that for lambda, except we don't really need lambda, right? What are we actually trying to solve for here?
The frequency, so you just plug that in instead, right?
Yeah, we can use that as a substitution because we know that velocity equals wavelength times frequency as usual. So that means lambda can be rewritten as V over F. Or since we've really got divided by lambda here, 1 over lambda would be frequency over velocity. So that divided by lambda, we can just replace with times frequency over velocity. So instead of divided by lambda, we're going to write this as times frequency divided by velocity. Because we're ultimately going to be needing to solve for frequency anyway. That's the final question here. So how would we start isolating F here?
Would you subtract pi?
Yeah, if we subtract pi from both sides, we get negative 2 pi times 6 meters times frequency over speed. 4 pi minus pi would be 3 pi. And I think I'm already seeing a problem here because when you solve for frequency, what sort of number are you going to end up with?
You'll have like a negative number.
Yeah, it looks like that's going to be negative. So, and we don't want to have a negative value for frequency. So that makes me think maybe we should go in the other direction. Maybe we should say pi, 0 pi, negative 2 pi. So let's call that negative 2 pi instead. So instead of saying this is 4 pi, let's say this is negative 2 pi, which is an easy fix. We just modify these equations. And then when we subtract pi, what do we get?
Negative 3 pi.
Yeah, negative 3 pi. And now it looks like this is going to work out well. We'll end up with a positive value for frequency. By the way, another way you could do that, instead of messing around with, is it 4 pi, is it negative 2 pi, we could have kept the 4 pi, but said, oh, we should have really subtracted the delta x in the other order. 1 meter minus 7 meters instead would give us negative 6 meters, which cancels out the negative, and we end up with a positive value for frequency anyway. Either way works, you're still going to get 3 pi on the other side when you subtract pi. And then what can we do next here? If we're ultimately trying to just find the frequency, what's our next step?
You could divide by the negative 2 pi times 6.
Yeah, if we divide both sides by, I guess that would just be negative 12 pi meters.
Yeah.
So, and the negatives will cancel out, the pi's will cancel out. So we just get 3 divided by 12 meters. So frequency over speed equals 1/4. And the units there would be inverse meters, or 1/4 meters. And then what else can we do here? If we want to find frequency,
multiply with the velocity.
yeah.
Do they give us that?
Yes, this is a sound wave. Multiplied by velocity, we just get speed over 4 meters. And this is a sound wave, so we can just use speed of sound, which in this case, I think it does specify, yeah, we're assuming the speed of sound is 340 meters per second. So we can plug that in. And meters cancel out, so we get 1/seconds, which is hertz, exactly what we should expect. And 340/4 would be 7085, I think.
Yeah.
So that would be the frequency of this sound, 85 hertz. Any questions on that?
Sorry, could you scroll down just so I could write down the rest of the question?
Yeah. Let me tidy this up a little bit. Yeah, that's the rest of the question here. And the louder than quieter than louder again is why we were able to specify destructive in the center, then walks towards constructive, then destructive, then constructive again. And that's why we needed to specify that this was specifically 4 pi or -2 pi, not just any even multiple of pi. We can be more specific. Any other questions on that one? And someone else was earlier asking for a review of the quantum mechanics equations. So let's look into that. Because there's a lot of equations to keep track of in quantum mechanics, and most of them I assume would be provided on a test. But the important thing really is knowing which is which, when you can apply each one, and what to actually do about them, and yeah, how they connect to each other. So looking at the important ones here, let me pull up some variables as well. We're going to need some lambdas. I think just lambda, right? Lambda and yeah, let's go with that. So one of the big ones is the one that really connects to everything. How do you add or remove energy from a system in the quantum realm? If you've got an atom that's low energy and you want to bump it up to a higher energy level, how do you give it more energy?
You could add like photons or light, right?
Yeah, shine some light on it, make sure a photon hits it. And as long as the photon has the right amount of energy, the atom will absorb the energy of that photon. So energy of a photon, specifically one photon, is going to be usually written as Planck's constant times the frequency of the light, or instead of frequency, we could write it as speed divided by wavelength. And speed, Planck's constant times speed divided by wavelength is often more useful, not always more useful, but for light, usually what we care about is the frequency, or sorry, what we care about is the wavelength. That's usually how light is described in terms of its wavelength, usually written in nanometers. And HC is specifically about 1,240 electron volt nanometers. Electron volts being a unit of energy, and nanometer as being the unit of distance. And electron volt is just is literally just charge of one electron as an absolute value times 1 volt. And 1 volt literally just means 1 joule per coulomb. So if you look up charge of 1 electron in coulombs, ignore the negative because we don't care about the negative, and then cancel out coulombs and write it as joules instead, that is 1 electron volt in joules. I would expect that in most cases you could just leave the energy in electron volts, but if you need to convert, that's how you would set up the conversion factor. Look up the charge of 1 electron. I think it's like 9 times 10 to the negative 30 something like that. But yeah, and Doppler effect, we can take a look at that if we have time. Yeah, I'm not sure we will, but we'll see. So this photon form, this idea that the energy of 1 photon is hc over lambda, this is pretty much universal. This is always how much energy 1 photon has. So you can always use that anytime you're talking about a photon being emitted by some system or a photon being absorbed by some system. And also the general idea that the delta energy of some system equals plus or minus energy of 1 photon. So that's going to be plus if the system is absorbing the photon or minus if the system is emitting the photon. But the energy of the photon is always hc over lambda. The energy of the system can follow different formulas depending on what type of system we're looking at. And what are some types of systems you've investigated so far? What are some kinds? Yeah, go ahead.
I'm sorry. Is it like when you have like a particle in box or?
Yeah. Let's start with that, the particle in a box model, and also the hydrogen-like atom. So if we investigate some of those, particle in a box, specifically one-dimensional box. So we're assuming we've got a particle in a long, narrow box. So it can move side to side, but there's no up and down motion, no forward and backward motion, just side to side only. In that case, the energy levels, anyone remember the formula for that amount of energy? Or what it's proportional to? I think that's the, if I remember correctly, h squared n squared over, 8m l squared. And the most important thing there, I think, is that the h is a constant, of course. H is a universal constant, Planck's constant. The mass of the particle is not going to be changing as time passes. The length of the box does not change as time passes. So if you think of everything else as constants, this is just a constant times n squared. And of course, that constant is going to depend on the mass of the particle and the length of the box. But the energy levels are just some constant value, specifically the energy in the n equals 1 state. Because if you plug in n equals 1, you just get that constant. So all of the energy values are something squared times that basic energy value. We could have, for instance, E1 is just itself. E2 is E1 times 2 squared. E3 is E1 times 3 squared. E4 is E1 times 4 squared. E5 is E1 times 5 squared, and so on. And one of the most important things about this is the changes in energy. And what happens to the change in energy as we work our way up the scale? Like from 1 to 4, from 4 to 9, from 9 to 16, 16 to 25. What's happening to those gaps? Yeah, those are increasing. From 1 to 4, that's a difference of 3. From 4 to 9, that's a difference of 5. 9 to 16, that's a difference of 7. These energy gaps are getting larger and larger and larger. As you go up the scale. So the higher energy it's in right now, the more energy it takes to get to the next slot. So on the usual diagram, that's going to look like we start with energy, some lowest energy possible. And then the next energy above that is pretty close. And then further, and then further, and then further still. And so as you go up the energy scale, it's going to take more and more energy to get to the next one. So that's what the energy graph would look like for the particle in a box model. Any questions on that so far? And then if you wanted to figure out how much energy is gained or lost, you would just subtract final minus initial. That would tell you the delta energy of the system. And you could set that equal to the energy of the photon being absorbed or emitted and solve for a wavelength. That would tell you, for instance, what wavelengths that system could absorb or emit. Any questions on that so far? And let's take a look at the hydrogen-like atom also. And by hydrogen-like, we basically mean a nucleus with one electron orbiting it. So you could have hydrogen with its usual one electron, or you could have a helium atom, or helium ion, I should say, because it only has one electron. Or maybe an oxygen atom that's missing 7 of its electrons, so it only has 1. So if you have a nucleus with one electron orbiting it, we would consider that a hydrogen-like atom. And that also has a formula for E sub n. And what formula does that use? Yeah, that is negative 13.6 times electron volts times z squared, where z is the atomic number, divided by n. I think that's actually n squared, right? And z, of course, is going to be a constant for any individual atom. Like if you're dealing with hydrogen, z is 1, and that's it. If you're dealing with oxygen, z is 8 and stays 8. So z doesn't change unless you swap to a different type of atom. Meaning, if we calculate some of these, E1 is going to be negative 13.6 times z squared. And then E2, the next one up the scale, is going to be that divided by 2 squared. So that'll be the same E1 divided by 4. And then E3 is going to be that same E1 divided by 9 instead. Then E4, E1 divided by 4 squared. E5 would be E1 divided by 5 squared, and so on. So in this case, we've got a negative number that's being divided by larger and larger values, getting closer and closer to 0. But if we were to set up a similar chart here, our lowest possible energy would be the negative 13.6. But the next one up would be 1/4 of that, which is negative 4 point something, 4 point, no, wait, is that it? Negative 3.4. And I'm going to mark 0 on this graph also, because 0 is the highest this can get. It's never going to get up to 0 or above 0. But as we go up, E2 is going to be negative 3.4. So that's a fourth of the way up to 0. And then the next one, E3, is going to be 1/9 of the original. So 1/9 of negative 13.6, that's 8/9 of the way up towards 0. And then the next one, E4, is 1/16 of the original. And next one, 1/25 of the original. So these are getting closer and closer to 0. And what's happening to the gaps? Yeah, these energy gaps are getting smaller and smaller. So this is one of the biggest differences between these two types of systems. For the particle in a box, as you increase the energy level, the gaps get larger and larger. It takes more and more energy to get up to the next energy level. For the hydrogen-like atom, if you're in the lowest state, it takes a large amount of energy to get up to state n equals 2. But then it takes less energy than that to get to n equals 3, and even less energy to get to n equals 4. It gets easier and easier to go up one more level as you get to higher and higher levels. And smaller energy gap means you need less energetic photons. For a photon, less energetic means longer wavelength. So to make the first jump from ground state up to the first excited state, you need a photon with very short wavelength and therefore very high energy. The next level, you don't need as much energy, so you can get a photon with a less energy and a longer wavelength, then longer wavelength, longer wavelength. So these very high levels, you can use long wavelength, low energy photons. These lower levels, it's a larger jump, so you need high energy photons, which translates to short wavelength. So that's one of the biggest differences between these two models. I mean, sure, they use different formulas, but the result of that is small gaps that get bigger versus big gaps that get smaller as you move up the scale. And also in the particle in a box model, there's no limit to these. You can just keep getting higher and higher and higher energies. For the hydrogen-like atom, what are these values approaching as we get to higher and higher n values? What's the highest the energy can be here? Yeah, 0. And physically, that doesn't mean the energy cannot go above 0. It just means 0 is where this system breaks down. You can certainly add more than 13.6 electron volts to the hydrogen atom. It's just that if you do so, if you bring that energy above 0, what do you think is going to happen to that electron? If you've got an electron in this hydrogen atom and you give it more and more and more energy, what do you think would happen to an electron if you give it way too much energy? Yeah, it's going to free the electron. All of these energy values are talking about an electron bound to the nucleus, an electron, I guess you could say, in orbit around the nucleus. If you give it more and more energy, that bond becomes weaker and weaker. If you give it enough energy, the electron leaves the system. It has enough energy to depart from the atom entirely. So if you give the electron exactly enough energy to bring it up to 0, the electron is able to leave the system. You have broken the bond. If you give the electron more than enough energy, if you bring it up above and beyond 0, the first 13.6 electron volts or whatever goes into breaking the bond. Anything beyond that, any leftovers, become kinetic energy. That is now not only a free electron, it is a free, fast-moving electron. And this is actually the foundation of how solar panels work. Solar panels are just a bunch of atoms set up in such a way that visible light from the sun, hits it and has the right wavelength to give an electron in those atoms the right amount of energy to leave the atom. Now you've got these free-floating, moving electrons, and that's electrical current. You just need to make sure it's directed into wires to be able to make it useful. And then the only other situation I've seen in 7C is the quantum oscillator model, if you just got a couple of atoms oscillating back and forth. And in that case, the formula was I think it was just some base energy times odd numbers. So you get like epsilon, 3 epsilon, 5 epsilon, 7 epsilon, all odd multiples of this base energy. And what pattern does that follow in terms of the increases in value? If you've got epsilon, 3 epsilon, 5 epsilon, 7 epsilon, what could you say about those gaps, those changes in energy? Yeah, those are all equal. From 1 to 3, that's +2. From 3 to 5, that's also +2. 5 to 7, also +2. So in the quantum oscillator model, the base energy times an odd number, those energy gaps are all the same size. So going from state 1 to state 2 takes a certain type of photon. State 2 to state 3, exact same type of photon. State 3 to state 4, or state 100 to state 101, they're all the same photon. So for the quantum oscillator, all the energy gaps would be covered by the same type of photon, same wavelength. Particle in a box and hydrogen-like atom, those are going to have differences because of the changing size of the energy gaps. Any other questions on that? All right, looks like we are out of time for today, but if you have any other questions, feel free to email me, and I'll also be in office hours 5:10 to 6 this evening. Good luck on the midterm, and I will see you next time.
Thank you.
You're welcome.
Thank you.